Hi, Lily. Just wanted to catch you up on physical science from today. And so this is your homework. You can just copy down the triangles onto lined paper, and that will be fine. So I will show you each of those, and I'm going to do one or two of them with you. Okay. You can expect a test on Thursday. It should be one that you're pretty well prepared for. Especially if you're watching this video and keeping up. But you're going to have some triangles on that test. Okay, some of those triangles will be doing what we've been doing, but some of them will be using inverse sine, inverse cosine, inverse tangent. And those are going to be ones where you know two sides, but you're trying to find an angle. Okay, because the ones before we've known a side and an angle, and we're trying to find another side with that. And so I'm going to do a few of those with you. That's going to be one part of the test, is triangles, just like these, okay? But another part is going to be to solve a Eratosthenes type problem. So where you're trying to find the circumference of a fictional planet. So you're going to do the same thing Eratosthenes did about the Earth, but you're going to do it with a fictional planet. And I'm going to go through an example with you, okay? So let's start with the triangles. I'm going to ignore that. I'm not really sure why all of that is there. But if I know that this is a right triangle and my hypotenuse is 5 and my side is 4, and I'm trying to solve that angle, so the angle that you see the little arc made in, that's the angle you're trying to find for each of these. These are not solved for everything type problems because you don't have a whole lot of space to work in, okay? So you're going to start by doing the same thing that we have been doing before. All right, if this is my angle and I know this side, that's the adjacent, right? And then that's obviously the hypotenuse. So what tool has the adjacent and the hypotenuse? I always have to do TOA still. So adjacent and hypotenuse, that's a cosine. So I want to use the cosine for this, okay? And that rule is cosine of theta, cosine of my angle, is equal to the adjacent, so is equal to 4 over the hypotenuse, which is 5. Okay. Now, 4 divided by 5, I can very easily turn that into a decimal. That's 0.8. So I could rewrite this and say cosine of theta is equal to 0.8. Now what I don't want to do here is find the cosine of 0.8, because that will not give me my answer. What I'm trying to find is, if I hit cosine of some number, what is going to give me 0.8? Okay? And so the way to do that is to find the inverse cosine of 0.8. So I know you were here, but just on this particular calculator, I have my sine, cosine, and tangent button. But then above them, with my shift key, is my inverse sine, my inverse cosine, and my inverse tangent button. Now what I think I need to do is hit on this particular one, the inverse cosine first, and then put in my 0.8. And then close my parentheses. So some calculators will make me do it this way. Others, I can have the number already on my screen and then hit inverse cosine, and it finds me the inverse cosine of that number. All right, this gives me 36.8 degrees. So equals theta. And so this angle here is 36.8 degrees. Now, if I were to do this again with a different trig function, a different inverse trig function, and find this angle, you don't need to do that on here, but if you want to check on just one or two of them, try it again with the opposite and the hypotenuse. So that's the sine this time. So the inverse sine of 4 divided by 5. So if I put that in my calculator, the inverse sine this time of whatever 4 divided by 5 is, that should give me another angle, 53.1. And Now, because of rounding, it might not be exactly 90, but these two should add up to 90 degrees, right? And let's see if they do. Does 36.8 and 53.1 add up to 90 degrees? 50, 60, 70, 80, 6, 7, 8, 9. It looks like 89.9. It looks like they're going to add up to 89.9. So I think with the rounding, that's 90 degrees. So that kind of tells me I did it right. Okay, I'm going to do one more. Now I got some room. All right, if this is the angle I'm interested in, I know the opposite and I know the hypotenuse. So opposite and hypotenuse. So I need the sine. So sine of theta is equal to the opposite over the hypotenuse. Now I'm just going to do my substitutions. Sine of theta, I have to write again because I don't know what theta is. This is what I'm trying to solve for. Equals the opposite, so equals 5, and the hypotenuse is 13. Now once I get to this point, if I have a calculator that works this way with where I have to put in inverse sine first, then what I can do is I can put whatever in the parentheses I want. I don't have to put a number in the parentheses. I could put my 5 divided by 13 in the parentheses and close the parentheses, and it'll do 5 divided by 13 for me first, and then take the inverse sine of it. So I could do it that way. 22.6. So theta equals 22.6 degrees. Now, these aren't drawn to scale, obviously. Like if that's 5, that's not 13. This would need to be a lot longer, right? Because 5 is less than half of 13, but it looks like it's more than half of the side. But if this side were really, really long, and that was only 5, and this side was really, really long, you'd think that would be a tiny angle, right? That would be a smaller angle. That would be a 22-degree angle. So yeah, that makes sense. Okay. So for other ones of these, you might need tangent or you might need cosine. So that is how you do these. Okay. Let me also go over the Eratosthenes problem for you. What you're going to need to do is I'm going to give you a fictional planet. And so I'm just going to make this planet up right now off the top of my head right now. Okay. I'm going to draw a circle for the planet. And it's going to be a word problem. So I'm going to say on a distant planet, there are going to be 2 cities, and the cities are this far apart. Okay. Now, however far apart they are, make them far apart on your drawing here. And it's going to be very similar. There's going to be an obelisk in one of the cities, and there's going to be a well in one of the cities. And wherever those 2 cities are, there's going to be some angle, right, that opens up to touch both of those cities. And we need to know what that angle is. And this is how Eratosthenes found out what that angle is. Because on a particular day, you had to wait for a particular day to do this, the sun's rays were shining, and they were all parallel to each other. Okay. Now it came down directly into the well, but at a city, another spot on the globe, the sun's rays did not shine directly down onto the obelisk. They hit at an angle. And when they hit at an angle, it made a right triangle, right? Because the obelisk was standing straight up on more or less flat ground, okay? And it made a right triangle. Now he knew the height of the obelisk, and I'm going to give you the height of the obelisk. Let's just say that it's 200 meters. And let's just say that the shadow is 180 meters. Okay, so it made a shadow that's a little less than the length of the height of the obelisk. Okay, and let's say we also know how many kilometers, let's call them, between the 2 cities. So let's say they're 450 kilometers. Okay, so there are two parts to this problem. Well, really three if you count just drawing the diagram. So when you read the word problem, you're going to set up the diagram and label everything. And that's going to be a portion of your points. So that's going to be pretty easy. Okay, that's going to be 10 out of your 15 points. Okay, for this portion of it, this whole Eratosthenes thing is going to be, 10 points and 15 is going to be the other. So it's going to actually end up being 25 points. Okay. So it's going to be 10 out of your 25 points. Just the setting up and labeling. So if you can read that word problem and know what the picture of the situation looks like, that's going to get you a good chunk of your points. Okay. So the first thing you're going to need to do is just what you're doing on the other side of this paper is you're going to need to use an inverse trig function to find what this angle is. I thought we needed to know what that angle is. Well, it turns out they're going to be the same. Those two angles are going to be the same because, as we said, the sun's rays are parallel, right? And so you have two parallel lines with a line going through them. And so this angle and this angle are going to be the same angle. And so he was able to use trig to figure out what this angle is. So this was the angle he wanted. So he knew the opposite and he knew the adjacent. So he actually needed tangent, because tangent of theta equals opposite over adjacent. Now he knew the opposite was 180 meters, and he knew the adjacent was 200 meters. Now these aren't the numbers that are going to be on the problem on the test, but it's just going to be the same procedure, okay? So the tangent of theta, the tangent of whatever angle that is equal to this ratio. So what I want to do is take the inverse tangent of that number of 180 over 200. And that's going to give me what my theta is. So I'm going to do that on my calculator. Inverse tangent of 180 divided by 200. I could do 180 divided by 200 first, get it as a decimal, and take the inverse tangent of that number. But it gives me 41.98 degrees. So 41.98 degrees. Okay, so the first part was drawing and labeling everything. The second part was doing this triangle part to get this angle. So if I know this is 41.98 degrees, I know that this is 41.98 degrees also. Okay, that's the second part. The final part is actually pretty simple. It's just a proportion. Okay, so we know that a full circle, the whole way around the Earth, is 360 degrees. And we know that I have just a portion of that, 41.98 degrees. Okay, I know that if I opened this whole angle up to half of the Earth, it would give me half of the circumference. Okay, and whatever part of a circle, whatever part of a full circle this is, the 41.98 degrees, that's how much of the circumference of the Earth I know. Well, I do know this portion of the circumference of the Earth. It's 450 kilometers. This is just a part of the circumference of the Earth. It's not the whole thing. So I'm going to write my 450 kilometers here. And what I'm looking for is the whole thing. So this is a proportion. This is a part of a full circle. So 41.98 is just a part of 360, and 450 degrees is just a part of x, but I know it's a proportional part, okay? I know the bigger I open this angle up, the more of the circumference I know. So I want to open I want to open up 41.98 all the way to 360, and I want to open up 450 all the way to whatever the circumference is. So I have a proportion here. So remember a trick for proportions. If I know three of the things, I take the two that are diagonal from each other that are actual numbers, and I multiply them and then divide by the thing that's opposite of the x. This times this divided by this gives you this. Okay? So let's do that. 360 times 450 equals a big number, but then I need to divide by 41.98. And so that gives me 3,858.98 kilometers. So that is the whole circumference of the planet. And so you're going to do the same procedure on your test. And so right here, you're just practicing a part of that procedure, which is the triangle part. All right. So again, let me just give you a look at all the triangles. And then you can pause the video and copy them down. And those are the ones that we did together. All right. And hopefully you can join us tomorrow and for the rest of the week.